Let's start this lesson by reminding ourselves of the properties of the Lambert's conformal conic projection to give it its full name. We shall look briefly at scale. You will remember that Lambert altered the basic perspective conic projection in order to reduce the scale distortion. So is it a constant scale chart or not? But our main concern will be with convergence and how chart convergence differs from Earth convergence. As we said earlier, you are not required to calculate Lambert scale changes in the same way that we did with Mercator's chart. However, what do we mean by constant scale? It is a loose term, but generally, if the scale is within 1% of the correct scale, we regard it as constant. It means that you can use a ruler to measure distances. There is no requirement for dividers. The scale error depends on the change of latitude between the standard parallels. There is an equation to work this out, but you are not required to know it. However, we have calculated some values here, and we are going to put them into this table. We'll start with a value of 5 1/3 degrees between the northern and the southern standard parallels. If the chart is constructed according to the 1/6 rule, 5 1/3 degrees between the standard parallels gives us a maximum scale distortion, even at the worst point of only 1/10 of 1%. Why have we chosen a figure of 5 1/3 degrees? Does it have some special significance? As a matter of fact, it does. It is the separation between the parallels of 54 degrees and 40 minutes north and 49 degrees and 20 minutes north. These are the ones used for the CAA UK half-million topographical series. So, if you were to measure a distance of 100 nautical miles on this chart at any point using a standard half-million ruler, you will be within 1/10 of a mile of the correct figure. So if we now look at a chart with 16 degrees between the two standard parallels, the worst-case scale expansion or contraction increases to 1%, the limit of what we would call constant scale. Remembering our 1/6 rule again, if we have 16 degrees between the standard parallels, how many degrees are there between the top and bottom edges of the chart? The answer is 24 degrees. This means that the bottom edge of the chart could be in North Africa at 36 north, and we could fly all the way up to the north of Scotland at 60 north, all on a constant scale chart. Once we get to a larger separation of latitude between the standard parallels, the scale distortion increases. 28 degrees between the standard parallels also has a significance for us. The Jeppesen series, which includes the ED6, uses standard parallels of 37 north and 65 north. They use these for the whole of Europe. But the ED6, which is centred around 48 north, is right in the middle of the two standard parallels. And with 3% scale contraction, a scale on the standard parallels of 1 to 500,000 is contracted to 1 to 515,000 on this sheet. So, a Lambert's chart is constant scale for applications with a small change between the standard parallels, but not for smaller scale charts where there is a larger change of latitude. We are now going to look at the difference between Earth convergence and chart convergence. Earth convergence, otherwise known as convergency, is the difference in the inclination between two different meridians on the Earth, or the change in a great circle track between two meridians on the Earth. Chart convergence is the difference in the inclination between two meridians on the chart, or the change in a straight line track between two meridians on the chart. Note that for chart convergence, we are considering the change in a straight line, but for Earth convergence, it is the change in a great circle track. The two are only the same thing at the parallel of origin. Here is a worked example using this idea. A straight line on a Lambert's chart crosses the 12 degrees east meridian at A, which is 40 north, on a track angle of 292 degrees. It crosses another meridian at B, further west, on a track angle of 283 degrees. The sine of the parallel of origin is 0.6. What is the longitude of B? Once we've got the diagram, write the equation down. Chart convergence equals change of longitude times sine parallel of origin. We know the chart convergence. The track changes from 292 degrees to 283 degrees. That's a change of 9 degrees. And the question has told us that little n is 0.6. So the change of longitude is 9 divided by 0.6. This is 15 degrees. So if A was at 12 east and B is 15 degrees further west, it must be at 003 degrees west. What about conversion angle? The difference between a rhumb line and a great circle on the Earth is called conversion angle and has the value of half the convergency. The equation is that conversion angle equals half change of longitude times sine mean latitude. However, on a chart, the difference between a rhumb line and a straight line track is not called conversion angle, but it does have the value of half chart convergence. Its equation is that half chart convergence equals half change of longitude times sine of the parallel of origin. Here is an ATPL exam question based on this idea. On a Lambert's chart, the constant of the cone is 0.8. A is at 53 north, 4 west. You plan to fly to B. The initial Lambert straight line track is 070 true, and the rhumb line track from A to B is 082 degrees true. What is the longitude of B? You treat these types of problem exactly as you would a conversion angle problem on the Earth, except that because it's a Lambert's chart, you are considering the straight line, not the great circle. If the straight line track is 070 and the rhumb line track is 082, then the angle between them is 12 degrees. This is half the chart convergence. Our equation is that half chart convergence equals half change of longitude times sine of the parallel of origin. The question tells us that the constant of the cone is 0.8. This is another term for little n, or the sine of the parallel of origin. Rearrange the equation to make the change of longitude the subject, and the change of longitude works out at 30 degrees. So, if A is at 4 degrees west, and B is 30 degrees east of it, B must be at 26 degrees east. This difference between chart convergence and Earth convergence helps to explain why great circles are concave to the parallel of origin on a Lambert's chart. Imagine a Lambert's chart. Take two meridians, say 20 degrees apart. Now consider three different latitudes, say 47 north, 45 north, and 43 north. The parallel of origin will be 45 north. Draw straight lines joining the meridians at these latitudes. You can see that the three rhumb lines, which all cut the meridians at right angles, are parallel to each other. And also the three straight lines are all parallel to each other, although at different latitudes. So, the angle between the rhumb line and the straight line is the same in all three cases. What is the angle between the rhumb line and the straight line called? It's called half-chart convergence. What is the formula for calculating it? The angle between the rhumb line and the straight line equals half the change of longitude times the sine of the parallel of origin. So let's now calculate it. The change of longitude is 20 degrees, and the sine of 45 degrees is 0.7071, which comes to 7.071 degrees in all three cases. Now a different question. Let's consider the angle between the great circle and the rhumb line. This is conversion angle. What is its formula? The formula is that conversion angle equals half change of longitude times sine mean latitude. Again, let's calculate it. For conversion angle, of course, there will be three solutions, one for each of the three latitudes. Now let's plot each of these angles upwards from the rhumb line at each latitude. This will give us the initial great circle tracks. At 47 north, it is about 7.3 degrees. At 45 north, the parallel of origin, it is 7.071 degrees, the same as the straight line. And at 43 north, it is about 6.8 degrees. Now let's also plot these angles in from the right-hand end, and draw the great circles joining them. This is why a great circle appears as a straight line at the parallel of origin, but is concave to the parallel of origin at any other latitude. The straight lines always make the same angle to the rhumb line, whatever their latitude. But the angle that the great circle makes to the rhumb line depends on its latitude. There's just one final point to make on this diagram. Look at the amount of curvature of the rhumb line compared to the straight line. It is approximately 7 degrees in all three cases. But look at the amount of curvature of the great circles compared to the straight lines. It is about 0.2 of a degree at 47 north and 43 north. It is a much smaller amount, about 1/30th the curvature of the rhumb lines. So, whilst you need to know that theoretically great circles are concave to the parallel of origin, in fact, for all practical purposes, including plotting, you can treat them as straight lines on a Lambert's chart. And now we will deal with just one more idea, which is often useful in dealing with exam questions. On this diagram, positions A and B are joined by a straight line, a great circle, and a rhumb line. At the meridian, midway between the longitudes of A and B, all three lines will have the same track angle. So, let's summarize. We looked briefly at Lambert's scale, but there was no requirement to calculate how scale changes. If there is less than 16 degrees of latitude change between the standard parallels, then Lambert's charts are constant scale, such as on this topographical chart. But for smaller scale charts, where there is a greater change of latitude, they are not. We saw that chart convergence is the difference in the inclination between two meridians on the chart, or the change in a straight line track between two meridians on the chart. This is the equivalent to Earth convergence, but reference to a straight line on the chart, not a great circle. We saw that there is an equivalent of conversion angle on the chart. It is called half-chart convergence, and it is the difference between a rhumb line and a chart straight line. We then worked through a couple of practical examples, and found that you treat these just like convergency and conversion angle problems on the Earth, except that the rules apply to the straight line on the chart, not the great circle. We then showed that this difference between conversion angle and half-chart convergence explains why great circles are concave to the parallel of origin. But we emphasized that whilst you need to know that theoretically great circles are concave to the parallel of origin, in fact, for all practical purposes, including plotting, you can treat them as straight lines on a Lambert's chart. And finally, we said that at mid-meridian, the straight line, the great circle and the rhumb line all make the same track angle. This concludes the lesson on Lambert's scale and convergence. The next lesson will consider practical plotting.